Electric charge is one of the most fundamental concepts in physics. It's the reason why atoms stick together to form molecules, why lightning strikes, and why your phone can charge wirelessly. Understanding charge is crucial because it underpins all of electricity and magnetism, which are essential for modern technology and our understanding of the universe. From the static shock you get from a doorknob to the power running your laptop, charge is at the heart of it all. Though we didn't realize it at the time, our earliest encounter with charge dates back to 600 BC in ancient Greece, when it was discovered that rubbing fossilized tree resin, or amber, with fur caused small objects to stick to it. This strange effect, which we now know as static electricity, remained a mystery for more than 2,000 years. It turns out that the effect is caused by extremely small particles that are incredibly difficult to detect. Specifically, we're talking about the particles that make up atoms. Atoms are around 10 to the minus 10 meters in size, which is 10 million times smaller than a millimeter. To give a sense of scale, in a single liter of water, there are about 10 to the 26 atoms. That's 100 septillions, or 100 trillion trillions. Within each atom, there are three types of smaller particles: protons, neutrons, and electrons. You can imagine them as simple little spheres. In the center of the atom lies the nucleus, which contains the heavier protons and neutrons packed closely together. Surrounding the nucleus are the much smaller and lighter electrons, which orbit around it. In reality, these electrons behave more like fuzzy clouds than tiny planets, but this is beyond what we care about right now. It's far easier to imagine them as tiny spheres floating about. There are lots of interesting properties of these particles, to say the least, but in this course, we're particularly concerned with one feature known as electrical charge. Protons and electrons have a fixed, non-zero amount of electrical charge. The electron has a negative charge, and the proton has an equal and opposite positive charge, a convention established by Benjamin Franklin in the 18th century. We call this fixed amount of charge E, which stands for the elementary charge. The electron has a charge of minus E, while the proton has a charge of plus E. As they carry this fundamental unit of charge, we therefore also call protons and electrons charge carriers. You may have also been wondering about a neutron all this time. As the name suggests, it is neutral, with exactly zero charge, so we won't worry about it too much here. Now, if there's one key rule to remember about charge, it's that like charges repel and opposite charges attract. Two positive charges push away from each other, as do two negative charges. But a positive and a negative charge will always attract each other. Again, there's no deeper reason why this happens. It's just a basic rule of how the universe works. We'll explore the strength of these forces in the next lecture, but for now, this one rule is enough. Let's delve a bit deeper into the idea that charge comes in discrete units. The smallest amount of charge that can exist is E, the elementary charge. This means that any charged object must have a charge that is an integer multiple of E. For example, an object can have a charge of plus 2E, minus 3E, or 0, but it cannot have a charge of 1.5E. This discreteness is due to the fact that charge is carried by discrete particles like electrons and protons. Now, as most everyday objects consist of around 10 to the 23 atoms, you might imagine that measuring their charge in terms of electrons is not practical. For these scenarios, we instead measure charge in the unit coulombs, named after Charles Augustin de Coulomb, who we will talk about more in the next lecture. 1 coulomb is 6.24 times 10 to the 18 elementary charges to 2 decimal places. When measuring in coulombs, we effectively treat charge as a continuous variable, but at the atomic level, when dealing with individual electrons, the quantization of charge is crucial for understanding things like atomic structure and chemical bonding. One elementary charge is roughly 1.6 times 10 to the minus 19 coulombs. Let's look a little closer at some everyday solid materials. Even if a material is a solid, the electrons within it are not necessarily restricted from moving around. Some solids, known as insulators, don't allow electrons to move freely, while others, known as conductors, do. Most electronic devices are made primarily from conductors, where charges are free to move. Examples of conductors include copper and aluminium, while insulators include things like wood or rubber. In this course, we'll mostly focus on conductors, where we can clearly observe and manipulate the movement of charge. Don't worry about why some materials conduct and others don't. That's a deeper question tied to quantum physics, and not something we'll go into just yet. Anyway, let's go back to the experiment we mentioned at the start and try to understand what is really going on when we rub fur on tree amber. It turns out that all this time we were manipulating electrons without even knowing it. As we rub fur on amber, electrons are being scraped off the fur and onto the amber. As a result, the amber becomes slightly negatively charged, while the fur becomes slightly positively charged. As a result, the amber attracts small, neutrally charged objects, which is why they stick to it. Now you might be wondering why electrons move from the fur to the amber and not the other way around. The answer is that amber can hold onto electrons more easily than fur can. In other words, the amber has higher electron affinity than fur, which means that electrons are more strongly held to it. By the way, amber translates to electron in ancient Greek. If you are curious about electron affinities, you can look up the triboelectric series, which is a list of materials from the highest affinity to the lowest. If you rub a material with a higher affinity with one with a lower affinity, the one with the higher affinity becomes more negatively charged, while the one with the lower affinity becomes more positively charged. This method of charging an object is more generally known as charging by friction. There are other ways to charge objects as well. Firstly, if you touch a charged object to a conductor, charge can flow between them until a sort of balance is reached. Specifically, this balance is when two materials have the same potential, which is a concept we'll discuss in a few lectures' time. Without going into details, electrons repel each other, and if they move into a region where there is less repulsion, they will naturally spread out there. This method is known as charging by contact. More interestingly, even if the conductor and charged objects are not directly in contact, just from being near each other, the charges inside will still rearrange. As we'll see in the next lecture, every charge in the universe interacts with every other charge. It's just that the interaction decreases as the charges move away from each other. For example, if we were to connect a conductor to a ground source, which allows electrons to escape by contact, and then move the negatively charged object near it, we can push electrons out of the conductor to leave it positively charged. This method is known as charging by induction. So overall, we can charge by friction, contacts, and induction. We should also be clear that most everyday objects are neutral by default, with equal amounts of positive and negative charges within. This is completely logical, as anything with a net charge inevitably attracts charges of opposite sign in one way or another, until the charge is balanced. There's one more thing we should note about each of these scenarios. Though charges move around, the total charge in the system is always fixed. Charge cannot be created or destroyed. This law holds in all known physical processes, from the atomic scale to the human scale. The total amount of charge in the universe is therefore constant and will never change, as far as we're aware. Let's summarize the key points in this lecture. Firstly, charge is a fundamental property of nature, carried by protons and electrons. Protons have a charge of plus E, while electrons have a charge of minus E, where E is the elementary charge. For objects on the human scale, we use coulombs, while for the atomic scale, we use elementary charges. One elementary charge is 1.6 times 10 to the minus 19 coulombs. The fundamental rule of charge is that like charges repel and opposite charges attract. Conductors are materials that allow electrons to move, while insulators are materials that do not allow for this. You can charge an object via friction, contact, or induction. Finally, charge cannot be created or destroyed, it only moves around. It is therefore conserved. So all of this gives us a starting point for understanding charge. But if we really want to control it, we need to understand exactly how strongly charges push or pull one another. That is, what force does one charge carrier exert on another? That's what we'll explore in the next lecture.